All right, welcome back. We're going to keep on talking about circuits and capacitors today. Specifically with capacitors, what we want to talk about now is what happens to the energy or how is energy stored in a capacitor circuit, and then also something called RC circuits, which are, as you might imagine, what happens when we combine resistors and capacitors in the same circuit. So just a reminder that essentially what a capacitor is it's a storage device that is placed inside the circuit. And what it stores, really, if you think about it, is it stores charge. And because we're storing up charge, then we're storing energy. And one of the main reasons we might do that is just to release it at some point to do work for it. To do work for us, I should say. So the energy that you store in the capacitor, you can think of that in terms of the work done by the battery on the capacitor. So the battery does work to force charges onto the capacitor, and then that stored energy we can then release it and use it to do other work later on. So it's in terms of the work done on the battery. So the formula we have for potential energy stored in a capacitor. Okay, so the potential energy, and we'll just use the term EP, and maybe you can call it EPC for capacitor if you want, is going to equal 1/2 times the charge times the voltage. Now, when you first see that, you might be thinking to yourself, well, that looks familiar, but maybe just a little bit different. If you recall last unit on electrostatics, you remember that we defined the voltage as being the amount of potential energy per unit charge. And so you could rearrange this and say, okay, well, so I've got potential energy equals voltage times charge. So these look similar, except all of a sudden I've got this 1/2 that's kind of jumping in the way here. So why is it that when we store energy in a capacitor, it's only 1/2 of the charge times the voltage? Well, one way to think about this is, again, go back to our little model of a capacitor that we have here. And so recognize that when I plug this capacitor into a battery, what happens is this. We can see electrons flow very quickly out of the battery, pile up on this first plate. And that's all well and good, except now what has to happen is those electrons, those extra electrons that are on my negative plate, they have to exert a force on the electrons on the top plate or on the positive plate. And the force that they exert is going to push them, is going to force them back to the battery. And because of that interaction, some of the energy that we gave the electrons, they have to use that energy to push their other electron friends back to the battery. And so essentially, we end up using some of the energy from the battery to do the work on the capacitor itself. So this process, as it turns out, is going to use up about half the energy. And of course, we could store that energy, and great, now it's stored, and then we release it in our light bulb. But recognize that half of the energy that we used to charge the capacitor was wasted from the outset, just by doing work on the capacitor. That would be dispersed as heat from our circuit. So that's all well and good. That explains the 1/2. But remember also that we have our equation for a capacitor, and we said, capacitance is equal to charge per unit voltage. So I could say that charge is equal to capacitance times voltage, and I could take this and sub it in over here to get another expression that says the potential energy stored is 1/2 of the capacitance times the voltage squared. Okay, so either one works. We tend to use the second one just because it's put in terms of capacitance and voltage, which we probably know about the circuit from the outset. Okay, so just a kind of a conceptual question here. It says we've got two parallel plate capacitors connected to a battery that maintains a constant potential difference between the plates. So what is going to happen to all of these values as we pull the plates apart? So we charge up the capacitor, and then somehow we pull the plates apart. What is going to happen in this case? And again, maybe it's useful to go back and look at this situation here. So I've got maybe my capacitors nice and close together, and I charge it up, and there's lots of charges on the positive plate and the negative plate. And you'll notice a few things here. We're going to put the electric field on. So the one thing to notice is as I pull these apart, first of all, recognize that these plates wouldn't want to move apart. I would have to do work on this system in order to stretch these plates apart. And that's a bit of a clue as to what might happen here. So first thing you notice is that the field between the two plates is definitely getting weaker. And the amount of charge that's built up on the plates decreases. because the voltage is constant, but the amount of charge decreases between the two plates, then the capacitance is also decreasing. We can see that here in this little top bar graph, that when they're close together, I have a nice high capacitance and that decreases. But also recognize that the stored energy, the energy is going to decrease as well. So essentially, I'm gonna do work on this system, and now I'm gonna have less energy stored in my capacitor. So for each of these things, for all these things, I think we're going to get a decrease. Okay, so remember, electric field we define as being the potential difference divided by the separation. So if I increase the separation, that's going to be a decrease in electric field. The charge between the two plates, we know the charge between the two plates is going to have to do with the capacitance, right? So we know that capacitance is going to equal charge divided by voltage. And as we saw, both the capacitance and the charge both decreased as a result of those plates being pulled apart. And then, of course, as we saw just a moment ago, our energy stored is going to equal 1/2 times the capacitance times the voltage squared. So even though the voltage stays constant, because the capacitance is less, then the capacitance also decreases. All right, so let's try a question here involving energy where we do a little calculation. It says two capacitors in series, 10 microfarad and 5 microfarad, are connected to a third capacitor in parallel of 20 microfarads. Find the total energy stored in the capacitors if it's connected to a 12-volt battery. So I'm going to draw this out first and foremost. So I've got a 12-volt battery to start with. And the first thing I know is that those first two capacitors, C1 and C2, are in series with each other. Then I'll connect those back up to my battery, C2. And both of those are in parallel with a third capacitor, which we'll call very creatively C3. So this first capacitor was 10 microfarads, and then the second one was 5 microfarads, and then this last one here was a 20 microfarad. So just a reminder that when we have our capacitors in series and parallel, they're each going to follow their own sets of rules. So one thing I can do here is I can redraw my circuit, and instead of looking at these two capacitors here in series, instead of treating them separate, I can think of them as being a single capacitor together. This is the same kind of trick we used when we looked at resistors in parallel. Just sort of made our life a little bit easier. So I could think about this as like CS, for example, and then this is C3. And I know that from my capacitor rules, I know that the total capacitance, CT, the total capacitance is just going to equal the capacitance of CS plus the capacitance of C3, because they're in parallel with each other. So what I might do is I might just sneak over here and solve for the capacitance of CS. And remember, CS follows this rule where it's our kind of our inverse rule. So it's going to be 10 to the negative 1 plus 5 to the negative 1, all to the negative 1. So CS is going to have a effective capacitance of about 3.3 repeater microfarads, which means my total capacitance for my whole circuit is going to be 23.33 repeater microfarads. I can now find the energy. Reminder that the energy, just like we looked at with Ohm's law, just like we looked at with our other circuit rules, you can either look at the whole circuit or you can look at just one part of it. So the total stored energy is just going to equal 1/2 times the total capacitance times the total voltage squared. I could find the charge or the energy of each individual capacitor and add them up, and they should add up to this exact same number, and this is going to be a lot faster. So I'm going to do it this way. So 23.33 and times voltage of 12 squared, and we end up, oh, I should point out, this is microfarads, so times 10 to the negative 6. Easy to forget those micros and nanos and things. But the total effective, the energy that would be stored in here would be approximately 0.0017 joules. So not a lot, but there we go. Okay, so a couple of kind of conceptual, sort of conceptual questions that I want to do. And this is where we get into this idea of RC circuits. So RC circuits, very creative name, as physicists always have for things, resistors and capacitors in the same circuit. How fun is this going to be? So I've got a circuit. You can see it there. It's set up. Now the EMF of the battery is 6 volts. Now I want you to remember for what we said before. The EMF, that's just like the total voltage. So the total voltage I'm saying is 6 volts, and the resistance is in the wires. So R1 has a resistance of 2 ohms, and then R2 has a resistance of 4 ohms, and then R3 has a resistance of 6 ohms. Okay, cool. And then the capacitor, I don't really know too much about the capacitor, but that's okay. What we're looking at here is it says, what is the current through the battery immediately after the switch is closed? And this is a really, really key point, immediately after the switch is closed. So let's think about this. So when I close that switch, the first thing that's going to happen, and I mean this switch right over here, right? When this switch closes, look at what happens. Right now, before I close the switch, I've got this circuit and current is flowing. Electrons are coming out of this space here, and then they're splitting and going through one path or the other, but then they're all coming back together, and then they're all going through and back to the battery, and then life is good. But when I close this switch right here, effectively what I've created is a bit of a short circuit. This pathway, this whole pathway over on the side here, this pathway has effectively no resistance. And I should point out though that it has no resistance the split second after it's closed. The very first electron that can have the chance to go down this pathway here is going to encounter no resistance all the way to the capacitor. And then the very first electron that gets bumped off of this capacitor is going to experience no resistance until it gets to this resistor number 1. So functionally what the capacitor does is it alters a separate pathway that has effectively 0 resistance for the first split second. Now, after the second, third, fourth, hundredth, millionth, billionth electron piles onto this plate, well, then eventually this plate, as we saw, is going to get full. Once this plate is full, then effectively the current is going to stop going down that pathway. So it's really important to understand when we're talking about RC circuits, when are we talking about? The split second after we close the circuit, well, then that's a 0 resistance pathway. And then a long time after we close the circuit, that's all charged up, and that's effectively an infinitely resistant pathway. So when we find it's looking for the, what are we talking about? The current through the battery immediately after the switch is closed. Well, in that case, my circuit is basically just this. It's basically just R1 in my circuit. And then all of the current's going to go around through the capacitor. It's going to skip R2 and R3. Now, you might say, well, does some tiny amount trickle through R2 and 3? Maybe, but because the resistance through the capacitor is basically 0, we're going to say that all the current goes through that. So we are talking about ideal circuits here. So V is going to equal I times R, which means I equals V over R. And I guess we're talking about the total here. And so all of the voltage initially is going to get spent on that R1 resistor, which means I've got 6 volts going through 2 ohms. So I'm going to have 3 amps flowing in that first split second. Now, question B, after a long time. So after a long time happens, again, this alternate pathway is no longer an option. Even though this switch is closed, no electrons are going to flow to that capacitor because it is effectively full. So after a long time, then the circuit is going to behave like it did before we closed the switch in the first place, where I'm going to have a total resistance. A total resistance is going to equal R1 plus the inverse of R2 plus the inverse of R3 all to the -1. So that's going to be a resistance of 2 plus 1 over 4 plus 1 over 6, 1 over that is going to be a value of 3. And so my total resistance is going to be effectively 5 ohms. And so now my current, my total current, which is going to be total voltage over total resistance, is going to be 6 volts over 5 ohms, which is right around 1.2 amps. Okay. Now it's important to notice we didn't do the calculation, but that would have been the current through the battery before I closed the circuit, and then I would have had a quick spike that would have drifted down back to that original current. So here's another question, again, using an RC circuit. And in the last example, I kind of like had this capacitor in parallel with these resistors, and you saw how that behaved. And now we're going to look at a situation where I've got a capacitor that's in series with a resistor. So I've got my circuit here, and it says initially the capacitor is uncharged. The switch is then closed to connect the battery to the capacitor. That's great wording there. So we're going to close that switch. And again, what's going to happen is current is now going to start to flow because we've got a complete circuit. And they want us to draw a graph of current versus time. Current is a function of time from t equal to 0 to a long time has passed. So basically, they want to draw current as a function of time. So there's current. And we're going to go from t equal to 0 when I just first close that switch to a long, long time away. Well, if you think about it, this is similar to the last kind of question, where when I first close this switch, electrons are going to come racing out of this, well, not racing, but they're going to come out of this battery. They're going to go around here through the capacitor, and then through the resistor, and then the capacitor itself, again, has effectively no resistance. The very first electron that gets pushed to the capacitor is going to require effectively zero energy to push its next electron friend back to the battery. So initially, we're going to get a really, really big current. So I'm going to start off with some really large value for my current that's going to be like way up here somewhere. My initial current is going to be some positive value. And then over time, though, think about this. Over time, as electrons pile up on the capacitor, then eventually it's going to get more and more full. It's going to be harder and harder to push more electrons onto the capacitor. So a long, long time away, I should have a very, very small current. And what we'll see here is we see kind of like this, going to drift off. Now this should maybe look familiar to you. This is something we call an exponential decay curve. So effectively, we start off at some large value and it drops off and drops off over time. This right here, this would actually be asymptotic. So technically speaking, it would get closer and closer and closer to 0 as it goes off to infinity. In functional terms, this is actually going to get to basically 0 and probably relatively quickly. You could ask the question, what is going to determine how long it takes for the current to basically drop to 0? And the answer to that is, well, it depends on the value of your resistance and it depends on your capacitance. If you have a very, very large resistor, then it's going to take a long time for the current to fill up the capacitor. And if you have a very, very large capacitor, well, then it's going to take a long time to fill up. So we sometimes talk about the RC value of the circuit as being related to time. Okay, you can think of this a little bit like the half-life, if you've studied anything around nuclear decay, is that the time it takes to fill the capacitor is going to be a function of both the resistance and the capacitance. Okay, so now it says sketch graphs of the voltage across the battery, the total voltage, across the resistor, and across the capacitor as a function of time from t equals 0 to t equal to a long time. I don't know why, I just like that idea of up until t equals a long, long time from now. So let's think what we're saying here. Is we're saying that, look, if I come along here and I measure the total voltage across the battery, okay, what's that going to look like? And then I measure, let's say, the voltage across this resistor. So maybe I'll call that VR for the voltage across the resistor. And then I'm also going to measure VC, the voltage across the capacitor. So what would all of these look like over time? Well, if you think about it, if you just ignore the capacitor for just a moment, we know that when we just had resistance in our circuit, we know that that followed Ohm's law. So the voltage across the resistor will just equal the current through the resistor times the resistance. Now the resistance is a constant, so the resistance doesn't change, but we did just see that the current changes. So the voltage across the resistor is actually going to mimic the exact same graph we just drew. So the voltage through the resistor is going to start at some large value and it's going to drop off asymptotically to 0. okay, or closer, and it's going to approach 0 for you limit fans, okay? So now that sort of makes sense, because if the current is decreasing over time, then the amount of voltage needed to push electrons through that resistor should get less and less. And so the question becomes, okay, well, what happens to the voltage measurement across the capacitor? Well, when I just think about how much energy it's going to take to put the very first electron on the capacitor, it's going to take almost no energy at all. Almost no voltage is going to be needed to put that first electron on. But each subsequent electron that we pile onto that capacitor is going to require more and more push in order to be convinced to go there. So my initial starting voltage is for my capacitor is going to start at 0. It's going to take effectively no voltage to convince the first electron to go, but it is going to increase over time, and it's going to increase like this. And this is like a different kind of exponential kind of growth. What we're actually going to do is we're actually going to like increase over time, but it's going to curve off, and eventually it's going to reach some steady state. Now, what's happened at this point? Well, a current has basically stopped. The capacitor is packed fuller and fuller and fuller, and then eventually that prevents any more current from flowing, which means in a way we're kind of using all of our voltage provided by the battery to pack those last few electrons onto the capacitor. And so what you might recognize is that these two graphs are kind of complementary. They kind of work together. And the fact that we start at some value up here and then we reach some peak value kind of gives us the idea that our total voltage, I almost drew a nice graph there. Our total voltage versus time is constant. The battery doesn't know what's happening in the rest of the circuit, so whatever voltage it supplies is going to stay the same, and you can use that wherever you want. This kind of leads us to the idea that the total voltage is really just the voltage used by the resistor plus the voltage used by the capacitor. Now, we saw that, or we know, I should say, that the voltage used by the resistor is going to be the current times the resistance. And from our rules about capacitors, we know that the voltage is really just the charge divided by the capacitance. So you can see here that as time goes on, effectively what happens is the charge builds up and builds up and builds up and gets larger and larger. And at the same time, the current decreases over time. And that explains those three graphs that we saw there. So last question is, after a long time has passed, after we've charged the capacitor, we're going to close the switch the other way. So if I go back to my circuit here, we're going to close the switch over like this. We're going to click it over like that way, and we're going to kind of cut the battery out, see you later. And it's asking, well, what's going to happen at that point in time? Well, recognize that while this was charging up, my top plate became my positive plate, and my bottom plate became, my top plate became the negative plate, and the bottom plate became the positive. And so what I'm going to have is I'm going to have a circuit that consists of a resistor and a charged capacitor and nothing else. So the reason that this capacitor was charged, I guess the reason it was staying charged, was because the battery kept that forward pressure, and eventually there was enough back pressure on the capacitor that the current completely stopped. But when we cut the battery out of the whole circuit, then what's going to happen is the electrons are going to be released, and they're going to travel through the capacitor and around and back to this plate here. Effectively, what we're going to do is we are going to discharge the capacitor. Okay, and all of the energy that we stored in the capacitor is going to get used up by pushing that current through the resistor. Now, if it wasn't a resistor, if it was a motor or a light or something like that, we could use it to do something more useful than just generate a bunch of heat. But this is effectively what happens, is that we're gonna reset this capacitor back to 0. Okay, that is it for our talk on RC circuits.